Okay, let's derive Coulomb's law from Gauss's law. So we're going to derive Coulomb's law from Gauss's law. First thing we're going to do, start with a point charge. Some charge, call it Q1. And we're going to apply Gauss's law to this point charge and the Gaussian surface that we're going to construct around it. We'll construct a spherical Gaussian surface around this point charge, a radius r, such that the Gaussian surface has the same symmetry as the E field of the point charge itself. So this is our Gaussian surface. And to this, we're going to apply Gauss's law. So the integral over this surface of E dot dA is equal to the charge enclosed over epsilon naught. Okay, well, everywhere on this surface, the E field will be going radially outward. So everywhere we consider away from the charge. And since it's a spherical surface, the area vector will be going radially outward as well. It will be normal to the surface everywhere. Hence, the E field will be parallel to the area vector everywhere on this surface. So that means that E dot dA will be equal to EdA cosine 0 degrees, because there will be no angle between the two, and cosine 0 is 1, so E dot dA will simply be equal to EdA. So now our Gauss's law on this surface looks like this. EdA is equal to the charge enclosed over epsilon naught. Now the charge enclosed is simply Q1. So we can say that this is equal to Q1 over epsilon naught right there. Also, we know that the E field is constant on this surface. There's no reason why it should be greater at any point as opposed to any other point, because the whole surface is the same radius r away from the point charge, and by symmetry, then the E field should be constant. Since it is constant, we can take it out of the integral, and we now have E dA over this surface is equal to our charge enclosed, Q1, over epsilon naught. But dA over the whole surface is the area of the sphere, and of a sphere of radius r. So we now have that E times 4 pi r squared equals Q1 over epsilon naught. Alright, sounds good. Solving for E, we have that E is equal to 1 over 4 pi epsilon naught times Q1 over r squared. If we let K be equal to 1 over 4 pi epsilon naught, which is our famous 9 times 10 to the 9 constant, so let's put that in there, then we now have that the E field is equal to K Q1 over r squared. Sounds good. That's the E field everywhere on our Gaussian surface, moving radially outward. We're almost done. Oops. Now, if we bring in a point charge, another point charge, bring in Q2 to our Gaussian surface. So now we have Q1 here, and then we have our radius, and then we brought Q2 and put it on that Gaussian surface. So now it's going to feel a force. And the force it feels would be equal to the value of Q2 times the E field that exists there. And that force would be radially outward as we've drawn it. So this force is equal to Q2 times E, which would be Q2 times KQ1 over R squared. And that's going to be equal to KQ1 Q2 over R squared. This is Coulomb's law. So we started with Gauss's law, and we applied Gauss's law to a Gaussian surface at radius r. Then we brought in a point charge Q2 to that surface, and we were able to derive Coulomb's law, which is the force between two charges. So that is our derivation.